Welcome to circuitvalley.com. I'm Gaurav, and today we are going to talk about analog devices slash linear technologies part, a linear regulator. In the context of I'm trying to make a second version of my hardware, this little hardware which you see in front of you, LM399 voltage reference, and in this voltage reference, I'm going to use this linear technologies slash analog devices part. This really nice ultra low noise, very high PSSR LT3042 linear regulator. This regulator is going to supply 15 volt to the LM399 voltage reference and its circuitry which amplify this voltage to a fixed 10 volts. This is the second version of my hardware which I previously built, which was very popular. And in this second version, I'm going to include a power supply. There will be few more components. This is a prototype, so there will be one more revision coming up afterwards this. And in this prototype, I'm going to evaluate LT3042 and I'm going to see how well it performs. So this little regulator which you see, this is the LT3042. I'm primarily interested in few parameters. I'm going to evaluate these parameters and see if how well it performs and how well it compares to the data sheet. I have made this tiny contraption here. These three MCX connector which you see there, these are input to the supply, output of the LT3042. There is one more regulator mounted there under this SMA connector, and it is from Microchip Technology. We are going to compare our LT3042 against this. So this evaluation is we are going to try to verify a few of the parameters. As said, I have a very limited amount of setup. I have very limited amount of instruments. So we are not going to perfectly evaluate every single things. For example, for measuring PSSR, you need certain setups and few equipments. I really do not have access to it. I have few equipments, one spectrum analyzer, one dummy load, a DC power supply, and we will try to use my function generator to inject a noisy source from this side and try to measure on the other side. Primarily, I'm interested in load regulation, how well the regulator holds its load how well the regulator holds its output when the output is loaded. So let's see. Let's go ahead. Let's connect the power supply here and see. Right now, on your screen, you can see LT3042 datasheet, and in this datasheet, we are going to verify few of the parameters, and let's look at the load regulation parameter. As you can see on your screen, its load regulation is specified from iLoad 1 milliampere to 200 milliampere with Vin of 2 volts and Vout of 1.3 volts. I have already configured this regulator to have an input of 2 volt and the output will be available on this port 1.3 volt. You can also probe the output from ground, and this really thick wire is also output. So we will try to connect our dummy load to this output. We can connect a spectrum analyzer. I have 3400B RMS voltmeter. We can also measure the noise of this regulator, but this regulator's noise is so low that it is beyond the range of what a 3400B, an instrument like 3400B can measure. So let's get on to it. I will show you the setup, what are we going to use to supply the voltage, measure, and what I'm going to, and let's get started. Let's take a look at the instrument. First instrument is going to be this power supply, HMC8043. This power supply is capable of delivering 100 watts. It also supports 4 wire modes from a connector on the back. This power supply is my trusty unit since many years. I'm going to use it as a power supply source. If needed, we can also use this little battery pack with 2 cells of 1.2 volts each. This battery pack will be used as really low noise source to the regulator in comparison to switching regulator. We can also use my 3400B to verify how much noise is my regulator is generating. But as I said, this particular 3400B is very precise instrument, but it doesn't go down to. But as I said, LT3042 is very low noise regulator. One of the best in its class. This regulator is so low noise that my 3400B will not be able to measure, but it will still try, and we'll see how it goes. I also have this Rodeon Charts RTB2004. This instrument also have a signal generator functionality, and on this signal generator I can specifically output a DC voltage with noise already pre-imposed on it. We can use this RTB2004 function generator capability to emulate a noisy power supply source into the regulator. As this is a generic function generator, it will not be able to supply much current, so we will not be able to put much load onto the regulator output, but it can be used to verify very minuscule amount of things, that how well the input capacitors and output capacitors affect the noise. If needed, we can use my 2005A. This is a linear power supply, pretty low noise, and this can also be used in comparison to a switching power supply for node 1 watts, and it can also supply really low noise source, but I think batteries will be enough. As a dummy load, I'll be using my Rigol LT3042A to load the regulator with current from 1 mA to 200 mA with a full range, and this instrument will be working in 4-wire mode. I'll be having this thick cable connected to the regulator output, and we will see how it goes. For some really low noise measurement, we can also use my spectrum analyzer to exactly look at the noise. Right now you can see the instrument is set from 9 kHz to 100 kHz. The first test we are going to perform is going to be line regulation. You can see on your screen electrical characteristics of the device and dial regulation parameter. You can see right here, V in 2 volts to 20 volts, high load is 1 mA and V out is 1.3 volt. Regulator is configured to output 1.3 volt. We'll supply 2 volts from here and we will see what's the voltage, and then we will supply up to 20 volts and we will see how well the voltage changes. So this is the probe, and I will connect it to output. First let me connect to the ground, and this is the output. Let's make sure that it's not shorted. Now let's connect the input supply. Positive need to go on this side and negative need to go on this side. Circuit is connected, and now let's connect my dummy load as well. Meter is connected. We will measure from this side and we'll supply the 2 volts from this side. This should measure exactly 1.3 volts. We'll see in a moment how much it measures. I'm going to connect a fixed 1 kilo ohm resistor on the output of this regulator, and we will see how does it work. We can also use this instrument in constant resistor mode, but on these low level of voltages and with such a low current of 1 mA, I think this instrument will not be able to produce very good results. So we have to rely on good old resistor load, and I'm going to produce exactly 1 mA of load on 1.3 volt. I have connected a 0603 resistor right here on top of that ceramic capacitor as a load, and I'll show you the power supply as well. So you can see the load has increased a bit. Previously it was 2.6 mA, now it's 3.7 mA, so load has increased a bit. We are still supplying 2 volts, and remember we are testing line regulation. So when we change this voltage from 2 volts to 20 volts, we want to see the output remain relatively stable, and it is allowed to change very little, and the amount it is allowed to change is only as per the data sheet specify, typically 0.5 microvolts per volt and maximum 3 microvolts per volt. This is what we are feeding in. 2 volts is consuming right now 2.6 mA. I have not turned on the load. As said, I'll be using my DMM7510, a really good 7.5 digit multimeter, and this multimeter on this particular range of 10 volts capable of only going down to 1 microvolts on the last digit, and we are, as per the data sheet, we are interested in a typical change of 0.5 microvolts per volt. So this 0.5 microvolt will be falling here, which is not being displayed. So I'll do a little bit more changes. So I will make input change significantly so that we can see the change. And as said, this typical specification is as said typical, and we can see maximum change of 3 microvolts per input volt. And let's see, get started. So right now it's outputting 2.9963848 or something like that. And let's go to the input and I'll show you what's the input voltage. Input voltage is 2 volts and it's consuming right now 3.9 mA. So let's change it. So first let me set it to relativity because we are interested in the relative measurement. So I'll set it to relative mode, and now it is showing you the display, and we already see the difference of around -1 to 12 microvolts. So you can consider it to be around 10-15 microvolts of noise. And let's see if I set the output input to 20 or maybe 10. Let's set it to 12 first, and then we will see how bad it goes. The current consumption has increased a bit. So right now we are measuring constantly around 14, 15, 16 microvolts additional. So you can say that, okay, for 10 volts change, maximum for 10 volt input change, maximum you were allowed 30 microvolts of difference, and it is less than this. And typical, if you go with the typical specification, you should be seeing 0.5, you should be seeing only 5 microvolts, but this instrument is not that kind of exact that it will be able to measure that. So we will go with the maximum specification. So it appears to be the regulator is performing within the spec. Let's go to the 20 volts and we will see how it goes. Let's go to the 20 volts and we'll see how it goes. So now we are supplying 20 volts, and let's look at the output. Output is -45 microvolts, -50 microvolts. We are allowed to change around, for the 20 volts input, you can do maximum, you are allowed to change 18 into 3, exactly around 54 microvolt. So it's not exact enough to measure this kind of stuff, but still we are within the spec, or at least borderlining the specification. So the next specification which we are going to test is going to be load regulation. We have successfully verified the line regulation. We changed the input voltage from 2 to 20 volts, and we verified the output stays within the limit, it stays same, and it only changes by around 50 microvolts. So everything is fine. Let's set the input to again 2 volts, because for the load regulation verification we are supposed to supply the load of 1 milliampere up to, and we will see how the regulation change. I will leave this 1.3k ohm resistor at the load so that it has some load available, and at least 1 milliampere load is there. I will keep my multimeter connected so that we can measure directly at the output. And now you should remember, even these small leads can cause a lot of drop in them. So even the contacts can cause a lot of drop in them, and 200 milliampere is not very much of a current, but still quite a bit of current. You should be really careful measuring such thing. The specification of the part, or data sheet of the part, specify the output on the pin, and these traces, and you see from here up to the pit part itself, it is few millimeters. So this induced resistance will cause issue, and we will see how it goes, and we will see how it affects us. So let me connect my load. So positive load is connected. Power supply input. I'm loading the instrument for around 9 milliampere, because the 1 milliampere load is already coming from the regulator, from the resistor, and you can see we are consuming around 8 milliampere or maybe 9 milliampere. It's buckling a bit because it's really low current, and this instrument is somewhat meant for higher current, but we can still verify our thing. Let's look at the input. I'll turn off my dummy load. Dummy load is turned off now. We'll take a relative measurement on this value, and we'll see how much the output voltage changes with the load change. Okay, so I will turn on the output load of 9 milliampere plus 1 milliampere, total 10 milliampere, and we'll see if the output load changes at all. So output has dropped around 40 microvolts with the load of 10 milliampere. Let's see the specification. The specification says load regulation V delta VOS is going to be maximum 0.5 millivolts with the load of changing from 1 milliampere to 200 milliampere. Right now we are at 10. Let's go to 100. So now we are at 100 milliampere load. and let's see how much the output has changed. Output had changed, dropped by 342 microvolts, so it is still less than 500 microvolt. But you must remember, the way we are probing this, we are a little bit away from the IC's output up to these probes. So I will remove this probe soon, and we will see if this measurement setup is causing this relatively higher reading. Let's first test, and we will measure with 200 milliampere load. Now I will change the load to 200 milliampere. Now load is full, 200 milliampere, and the output is topped around 696 volts. So it is out of the specification, but I will show you that it is not because of the chip is faulty, but it is primarily because because the way we are measuring a little bit away from the chip, and those traces, they are causing drop in the voltage, and we will see how it looks. So now I'll remove these probes. Maybe I can leave the ground connected. Let's turn off the input first. Input is turned off. So I have disconnected my multimeter, and I will now use this sharp tip to directly access the output pin. Let's see how easy or how hard it is. Let's get this thing out of the way, and I'll try to measure the output pin of the regulator. So now I'm exactly measuring the output pin of the regulator, and I'll show you first, and I'll show you how much it drops now. So you can see on the screen, load is still around 200, and my voltage output is dropped only by 460 microvolts. So we are within the specification. My measurement setup still may be not the perfect, because that is DMM7510. Last digit is pretty much insignificant, pretty much lost in the noise. So we should be able to trust this measurement. So we are well within the spec. Even the load change of 1 milliampere to 200 milliampere, output remains the same. Even though I do not have any good setup to measure PSSR or noise, but we can still try to use my spectrum analyzer and my 3400B to see if this instrument generates any significant amount of noise. So let's get started. Let's remove the multimeter, and we will connect our spectrum analyzer and true RMS multimeter to see if there is any significant amount of noise is being generated. I'll be using this MCX to BNC cable to connect my 3400B to this instrument, and let's see how it goes. Let's first measure the input. It's connected to input. Right now it's set to 300 volts. Let's change the range to 0.1 volt. So now we are at 1 millivolt range. And at the moment input terminal is shorted, so you can see the needle is going almost zero. That's inherent system noise of this instrument. It's not completely zero, but it's almost zero. 1 millivolt range, it's going to be around 30 or 20 or 30 microvolts RMS inherent noise of the system. Instrument 3400B has a bandwidth of 20 megahertz, and the noise specification of LT3042A specifies all the specification output noise specification at full load of 200 milliampere. So we have the full load connected still, the dummy load is still connected, and the frequency range is specified up to 100 kilohertz, 10 kilohertz to 100 kilohertz. We will not be able to measure that with this. We will not be able to specify the exact bandwidth with 3400B because I do not have a appropriate filter for that. And so what does it say? It says you can expect the output noise on the output of 3.3 volt around 1.9 volt RMS, as you can see on your screen, and on output of between 1.3 to 15 volt 0.8 volt RMS, and on output of 0 to 1.3 volt around 1.6 volt RMS. So you can see this instrument is capable of measuring around 30 this instrument 3400B is incapable of measuring such a low noise, so we will switch to my spectrum analyzer and we will try to measure it there. Let's select the frequency from 10 kilohertz to 100 kilohertz and we'll see how it goes. I set reference level to -90 dB, attenuator is set to 0 dB, and preamp is on for this small signal. Bandwidth is set to 10 Hz so that it can sweep at least in a reasonable amount of time from left to right. You can set the bandwidth to even lower, but then it will take 700 seconds so that it can sweep from left to right. Maybe 10 Hz for the sake of this experiment is tolerable. The noise floor doesn't go that significantly down. You can see on the left side, it goes a little bit down if I set the bandwidth to lesser, but it's not that much. Remember, we are talking about very low voltages. So with the RMS of 1.8 or from 1 to 1.8, you can expect the signal of peak to be around 100 dBm. Around 1.8 RMS is around 100 dBm and 0.8 RMS is around 110 dBm. So we'll see something here if the noise floor increases, and we'll see how it goes. First I will connect my instrument, its input, to the input of the regulator, and we'll see how it goes. You are not supposed to supply very high voltage of DC into spectrum analyzer's input. This spectrum analyzer's input is AC coupled and specified the DC voltage of maximum 50 volt DC, and we are supplying around 1.3 microvolts. We are supplying around 1.3 volts. We are supplying exactly 1.3 volts. You can see on your instrument the noise floor has increased significantly. Previously we were seeing around 30 lower than this, and it has increased. So this is the input of the connector which is supplied. This is the input of the regulator which is supplied by the power supply, and let's go down. So let's change it to the output of the regulator. I have changed it to the output of the regulator. You can see the noise floor has decreased significant amount, still around 110 or 100 dB. This little spurious pulse which you see, I think is coming from my power supply or my the instrument setup here. This is not supposed to be there. It's inherent noise in my test setup and everything, and it's not because of the regulator, and this you can significantly ignore. And you can see the output noise floor has decreased around 30 dBm. That's it for this video. We have verified the line regulation, load regulation, and the noise characteristics of this amplifier. I think it's already long enough video, and if you are interested, I can do more tests. Please let me know in the comments if I did something wrong. I'm not an analog buff, so if I did something wrong in the video, please let me know in the comments. Thank you. Bye bye. Visit www.circuitvalley.com.